Hi, everyone. Really excited to be here. My name is Franka, and I'm going to talk about homoiconicity in Clojure today. So I was at Polycon for the first time last year in Poznan, and I had a really good time there. I learned about the history of F#. I learned about how to use OCaml, and a lot of things about some other programming languages, some of which I'd never heard of. So because of that, I'm especially excited to return to Polyconf this year and be here on stage and chat with you. So I've been a Clojure programmer for a bit over 2 years now. And while hanging around Clojure programmers and just being active in the Clojure community, I often heard this saying, code is data and data is code. And while that sounds deceptively simple, I, for a long time, didn't really understand what that means. So what better way to kind of really understand a concept than to write a talk about it, right? So that's what I did. And yeah, so we're here today to learn about homoiconicity in Clojure and some really bizarre and cool things you can do about it. We're going to see some self-mutating code, and on the other side of the spectrum, we're going to see some actually self-healing code. And there'll also be some visualizations and some art things. First, a few things about me. Again, I'm Franka. I just started as a platform engineer at Mapbox, so if you want to talk about maps, come find me later. I cycle, code, live, do all the things I do in Berlin. And then I'm an organizer of Clojure Bridge in Berlin. Clojure Bridge, if you haven't heard of it, is an organization that helps underrepresented people come into tech, learn to program, and just generally have a community that they're welcome in. And Clojure Bridge is really the reason why I'm here today. Why, when I first started as an engineer, I found a lot of support and friends there. That's why I want to give a second shout out to them and really encourage you to support your local Clojure Bridge, or since this is a polyglot conference, support Scala Bridge, Rails Girls, whatever similar kind of initiatives there are in your language community. Yeah, it's just really a good thing to do. Donate your time or your money if you have a company that has money, and get people like me and other underrepresented people to be comfortable. One more quick organizational thing before I start. There's some GIFs and moving images in this talk. And since this is a huge screen, I'm going to be using the Dizzy hashtag to call them out before, in case you're sensitive to that. Watch out for this hashtag on the bottom lower left corner of the screen on the slide before the GIF, and then you know how to look away, or whatever is right for you. OK, let's go back to the opening statement. Code is data, data is code. So what people talk about when they do this is the concept of homoiconicity. And the best way I've come to understand homoiconicity is that it means that in a language that's homoiconic, the data structures that are available to program in that language or to use for data are the same data structures that programs themselves are represented in. So I'm going to be talking about Clojure because that's the background I have. But Clojure is a flavor of Lisp, which is kind of where the idea of that concept comes from. And there's a few other languages like Racket or Scheme around that also are homoiconic. So just you're aware of that. It's not unique to Clojure, but it's a really cool feature of Clojure. In fact, I'm going to argue today that homoiconicity is actually Clojure's superpower. And hopefully you'll understand what I mean by that later. So if we go to clojure.org, which is an introduction site about Clojure and has all the docs and stuff, it says there, Clojure is a homoiconic language, which is a fancy term describing the fact that Clojure programs are represented by Clojure data structures. And that dual representation is the concept that I really want you to keep in mind throughout this talk and think about what homoiconicity means. So the term itself actually references this dual representation. So homo comes from Greek for same, and icon comes from Greek for representation. So again, we have like code and data being represented as the same types. Let's look at an actual code example in Clojure to make this more concrete. So here we have a form in Clojure. And even if you haven't seen Clojure code before, you can kind of deduce what this does. We have a REPL there as well, which would evaluate it. So we have a function plus and two numbers, 1 and 2. And what you can kind of recognize intuitively as a programmer is that here we're adding two numbers and getting the sum of them 3. So there's two ways, actually, as a Clojure programmer, you can look at this form. You can look at it as a piece of code that you want to be evaluated and executed. You have a function plus, and you're giving it some arguments, 1 and 2, and you want to get the result of the function. That's the one way to look at it. But you can also choose to look at this form as a piece of data, where actually this is a list in Clojure with 3 elements, the first element being a plus, and then the 1 and 2. Slightly more complex example, we have a def here, time till coffee break, which is, I think, like 5 more talks, and some random time that you're going to be standing in the queue. So something like, actually, I didn't update the number, so that 64 is wrong, I just realized. It's something like 160 minutes. But yeah, so either you look at it as a piece of code and you're saying, oh, we have a def time till coffee break, and we're binding some number to that def to use it later. Or what we have here is a list of a bunch of expressions like def, the time till coffee break, and then another list, which in itself is another list of a plus and an expression and so on. Okay. So I mentioned a bunch of times already that it's about using the same data types. And before I move on, I want you to understand what these data types actually are in Clojure. So in Clojure, we use EDN, extensible data notation. And it's the set of types that Clojure knows. So the first ones on this list are kind of what you would expect, like integers, strings, simple data types, booleans like true and false. And then we have things like lists, which are denoted by parentheses, or vectors by the square brackets, and maps. And there's some other ones that I didn't include here. EDN is not exclusive to Clojure. It's just saying this is a set of types. You could also decide to use EDN in a language that you're using. Okay. To summarize again, Clojure programs are represented in a superset of EDN, and Clojure programs handle actually data that is a superset of EDN. The superset part, you don't really need to worry about that. I just included it to be precise. So a lot of times when people hear homoiconicity, they first think about macros and metaprogramming. But I really, after thinking about this topic and reading about it for a while, I really sort of felt that one of the most important things is about the point that Clojure is a data-first language. So languages normally are optimized for writing code rather than manipulating data, because they're written for programmers to write code, and so it kind of makes sense that, you know, you want things to be easy for programmers writing code. But in Clojure, we really care about data and manipulating data. That's actually what Clojure is kind of known well for. And so there's kind of this trade-off, like you want code easy to write for programmers, but you want data to be easily written as well. And one way to make these two things really equally well is to make the language homoiconic, because then when you're writing code, you're also writing data, and vice versa. And there's a blog post there, a link that summarizes this really well. Okay, so do you know that saying, when you have a hammer, everything looks like a nail? I want to introduce you to two kinds of hammers that make things look like two different nails. So the first one we want to look at is quote. What the quote hammer, as I like to call it, lets you do is to treat a form as data. So let's take this form that we looked at before, +1 and 5. We typed it into the REPL here, so the REPL evaluated it right away and gave us the number 6. So actually, it didn't treat it as data, it treated it as code. Because that's normally, when we're typing things into the REPL, that's kind of what we want to happen. But what we can do is call quote around this thing, and then what it's going to do is, oh, okay, we want to treat this thing as a list, so it's just going to give you the same list back. And it's saying, this is a piece of data, here's the data you gave me. And a shortcut for the quote function is just the single quote. And watch out for this single quote operator, it's going to appear a bunch of times in this presentation. Eval is the other hammer, and what eval does is to treat a form as code. So here we have our same expression again. Actually, what's happening implicitly is that it's being evaluated. If we have this quoted expression from before, it's not being evaluated. We're just getting the quoted thing back. We could now force it to be evaluated by calling eval explicitly on this form, on the quoted form. So let's try that. Okay, and then we see, okay, we get the 6 back, which is what we wanted. Okay, so this might seem kind of obvious to you now, like the two kinds of ways to look at a thing. The most interesting part of this eval and quote duality is actually what happens when you don't use them right after each other, like I did in this example, but when you instead use them to delay evaluation or keep a piece of code that you want to have as data for a while and then evaluate later, for example. So there's some really interesting things that happen in the space between when you decide to treat something as code or as data. And there'll be more concrete examples of this. So macros, I want to talk about quickly. So macros are a way to extend a language by creating new constructs the compiler understands. So they're actually really common in Clojure programming. Even if you've never written your own macro, you've probably used one. So examples of this are or, and when, which some of these I think in other language wouldn't be a macro, they would just be in the like main language. So yeah. So let's look at if not. So if not is a macro that's actually composing if and not. So we can use the call macro expand to type in our macro and see what the compiler is doing underneath. So on the first line we say like if 41 is not an even number, say it's not an even number, which is exactly what we would expect. And then we can call macro expand on this whole form and we get the expanded macro back. Here's the first instance of our quote operator. At this point, we don't want this form to be evaluated. We just want to say, take this expression, treat it as data, and tell us more about it by expanding the macros in there. Another example, so we have a number 42, and we have like this expression, when 42 is even, give us back it's an even number. You can't see the whole line, sorry. And you'll get back 42. If you call macro expand with the quote operator, you'll see that when is actually just a shortcut for if do. So do lets you do multiple statements in Clojure. What would happen if we forgot the quote operator here? Maybe think about that. So kind of nothing would be expanded. So what would be happening here is instead of macro expand trying to expand the form, actually we would start evaluating it. By the time we hit the macro expand function call, it would just treat trying to macro expand 42, and there's no macro on 42, so it just gives you back 42. So this is an example where the quote operator, to delay evaluation, or in this case of the first line not have evaluation at all, is really useful. So takeaways from the first section. Homoiconicity, code is data, data is code. That's yeah, what that stands for. So Clojure is really data-oriented and puts data first, and homoiconicity reflects that. Quote and evals are two hammers that lets you look at forms as either code or data, depending on what you need in that point of time. Lastly, we can extend the language of writing macros, but I really want to stress that homoiconicity in Clojure is not just about macros, it's more about putting data first, and there are other things you can do with it. Okay, now we're going to start with the adventure talk of the part of the talk. I'm going to talk you through a series of examples where homoiconicity does cool things. Oh, okay. So let's again go back to code is data, data is code. So what can we do with data? If you think about like data as some numbers or some spreadsheets, or yeah, what can you do with those? One thing is you can visualize it. You can draw graphs, make patterns, do visualizations, all those cool things. You can analyze it. You can, again, like try and find patterns in the data, come up with formulas, etc. And finally, if you have a data set, it's really easy to generate data that extrapolates on patterns from your first data set. So what could we do if code is data? We could visualize our code, analyze our code really well, and also generate more code. Okay, the first project I want to talk about is one that I did, and you can find the code at this GitHub link. So the idea for this project was I wanted to do a visualization. So at Clojure Bridge, we use Quill, which is a Clojure wrapper around processing, to teach people Clojure. And it's a nice tool to do visualizations easily. So I was thinking about homoiconicity one day, as you do, and I was thought like, oh, it'd be really cool if you had a program that could visualize some kinds of things about the code that the same program is, like kind of visualized stats or things about itself. And I wanted to try to do this in the simplest way possible. So this is kind of a screenshot of what it looks like. So you have it's a bit abstract, so I need to explain it to you. So you have some dots on the left, and the dots represent one function in this namespace. On the right, you see the namespace. It's called visualize code.core, and you have the function count. So there's 12 dots, and it says the function count is 12. We also have a purple background, and that's kind of the visualization part. So I wanted to see, as I'm adding more functions to this namespace, aka I'm working on my program and developing more things, I want the background color to change, and I also want new circles to appear to show me how I'm making progress. So how does a program visualize itself? That's kind of a really abstract idea. I wanted to start just finding a simple metric. So I was like, okay, the number of functions or number of devs actually in a namespace is a nice and simple metric to start out with. Yeah, and then just visualize it. Okay, so now let's look at what this looks like in life, I guess. So on the right side, you have the picture that I showed you before. And on the left side, you can see me like typing out some function calls. And it takes a while, but you can kind of see how the color changes as the functions are uncommented and how more circles are added to the graph while it's happening. So yeah, I was really excited. Like I was, and of course, like it's connected to a REPL, so you don't need to restart it or save it. You're just evaluating the new functions that you're adding as you're going, and Clojure will pick up on it. So I was pretty excited about that. Here's how it looks like in the code. You have to require the namespace, of course, and then you have this helper functions to switch to this namespace. There's a variable ns that gives you the current namespace, and that's an object, and I wanted it as a string, so you convert it to the string. And then I use this function nspublics to give me all the functions that are in this namespace that I'm currently in. And then finally, I get all the this is in like a different format, so I'm getting all the keys from that map, so I get it as a list. Okay, and then I have a list of all the function names, and that I can use to count them or to do other things with them. And in the actual Quill sketch, we get the namespace by saying current namespace, ns, like this. And then so Quill has this functional mode where you can have a state that you can put stuff in that you need for drawing and updating your visual. So I'm putting the function count that I'm getting from the namespace into my state in order to be accessing it in the draw functions later. And then this is how I actually draw the background. It's getting the function count out of the state, and then just doing some number manipulation and putting it into a hue color value to change the background. And that's kind of it already, which is nice. It's not a lot of code. And then the circles, you're just drawing as many circles as there is for the function count. I use the NSPublics thing. There's also NSRefers, NSAlias, some other functions. And of course, you could do other things beyond this very simple metrics of how many functions in a namespace. But it was a nice experiment to get started on this topic. So some takeaways. It's super easy for Clojure program to read other Clojure programs and even read itself. The other thing is, once you have some kind of data about your program, like for me it was the function count, visualizing it is really trivial. You know how to visualize data, and it doesn't matter that this data used to be code or comes from your code. Okay, the next part is dev tooling and testing. During my research about homoiconicity, I stumbled over this quote by Joseph Wilk. One thing I really appreciate with code as data in a language such as Clojure is the power of your editor. The power of an editor is related to how well it can interact with and analyze code. And that really opened my eyes, because I kind of realized that, yes, exactly, the reason that why we have so many cool dev tools and the repo and live evaluations and can do live coding like the one I showed in my sketch is because our editors can interact and analyze our code on the fly really easily, because code is data and we can just understand and analyze it. I thought that was really interesting. And this is kind of like why we love Clojure, like all the cool dev tooling, like the flexibility of the repo, powerful editors with this inline evaluation, and live coding. And these things are because of the homoiconicity. Okay, another part that's marginally related to sort of the developer experience is testing. So actually last year, I heard this talk by a friend, Jan, about mutation testing. And he brought up the question, who tests our tests? Right, so you have tests to test your code, but who tests your tests? Like, how do you know that your tests are actually correct? And he introduced me to this testing technique called mutation testing. The idea of mutation testing is to mutate your code in order to test the completeness of your test suite. To paraphrase, you're kind of breaking your own code intentionally in order to see if your tests catch it. So if you break stuff in your code and your tests don't catch up on that, that clearly shows that something is wrong with your tests. They're not complete, or they're testing the wrong things. What kinds of mutations, as we call them, can you do? There's some simple ones, like you can switch around operators. For example, exchange plus and minus, and it can have like quite devastating impact already. For example, oh, I said plus and minus, or greater than equals than, in these examples. You could change if to if not, and suddenly like changes the entire meaning of what you're trying to do. Another bit more radical mutation you could do is just delete entire form. So if you had a function like here that does some maths with A and B, if you just deleted the entire content of your function and just returned an empty list, would your tests still pass? And if yes, you should fix them. So here's the actual mutation testing library by Jan that I looked at. You can find it on GitHub, again, on that link. And just a quick look at the internals of the library. So one thing we do here, for example, in the greater than to greater than equals swapping. So I mentioned that would be an example of an easy mutation to do. What we do here is we define this greater than either switch, and then we call the function swapping mutation, which swaps out the actual code. And all we do here is just passing these two operators as data into this function, which shows how easily we here, like, sort of on the fly, taking a piece of code, treating it like data, like taking out some part of the data and putting something else in instead. And there's some more examples, like you could change and or, again using the operator to say we're treating code as data here. Empty seek or equals and not equals is also an interesting example. The takeaways from this section. So some cool things about Clojure dev tooling, the REPL, powerful editors, live coding. These are really due to the fact that we can analyze our code like data easily. Yeah, homoiconicity is the base for awesome dev tooling in Clojure. Another thing, mutation testing, where we generate and regenerate and change a code as if it was data, or because it is data, rather, is really simple. All right, let's move on to the next part, the Tweety bot by Roger Allen. This actually also features Quill, which I mentioned in the first example, and it uses it to visualize code, or sorry, not to visualize code. It does visualizations, visual art pieces, and it does so by generating code over generations, and just having some random factors in there and creating images. And then there's a Twitter bot that tweets out these images at random intervals. So here's what an example tweet could look like. We have the picture that's generated, and it's still live. You can follow it on Twitter and get nice images in your timeline, which I like to do. And then there's some info in the tweet, like the name of the file, and there's a link to a gist. If you click on that link, you will get to something like this. So this is a section of a gist, and it's all of this is metadata or data describing this image that we just saw. So there's some things to be expected, like the name of the Clojure file, where we ran the code that generated this image. There's the parent, so I mentioned it's a generational generative programming algorithm. There's some other like hash numbers, I'm not sure what those are. But then the interesting part is the last point, the code. So what we have here is the exact code that was used to generate this image, and we just throw it in this hash as just another data point about this image. And so what this lets us do is really reproduce this image super easily. So luckily, Roger, in the README for this project, has a really nice introduction on how to reproduce it. So I wanted to try it. So we get the code from this image. It's literally just copy-pasted from the gist. And we throw it into a dev code. Again, using the quote operator, because we don't want to evaluate the code just yet. We're just saying this is the code used for this image, like kind of save it for later. And then what we do is we run this function show. We then evaluate the code at this point, because now is when we actually want to show the image. And then we give some parameters, like the height and the width of the box. And there you go. That's the exact same image from the tweet before. And I thought that's really awesome. Like, you just have this code, you copy it, you run it, and it works. So we can really share, store, and reproduce data like this super easily. Since code is data, and in this case, it was literally just a piece of data attached to the original picture object. And that lets us do really cool stuff. Okay, I need to hurry up. We can generate code like data through generative programming really easily. And it's really great for generative art, as you saw here. Okay, Clojure spec. So Clojure spec is a library introduced to Clojure in Clojure 1.9. Things you can do with it include describing data using specs, validating data against these specs, and generating data from specs. The last project I want to talk about is Self-Healing Code by Karen Meyer. If you haven't watched this talk, you should really do it. It was given at Your Clojure 2016. It's online, and so is the code. And she talked about this concept of self-healing code that can heal itself by transferring software from a working code base into some place where code is broken, to summarize. So example, we have an average calculating function, takes a vector of numbers, calculates averages. Normally it works as expected, but when you give it an empty vector, it breaks and it throws an exception. Because obviously what's happening here is it's trying to divide by the length of the vector, the length is 0, so then we throw an exception. To summarize the self-healing programs here, I'm not going to go into detail how Karen did this, but the summary is you need to recognize when a failure actually occurred. Did something even go wrong? We need to see that exception. You need to find out where this failure came from, which function and which input. you need to pick the best batch from a given selection. So you're assuming you already have a code base that's working where you can pick a selection from. You need to actually pick the best one to apply. And finally, you need to do the actual replacement of this patch. So just, I'm skipping over a lot of like work here, but really then what you see as the result is you have this healing namespace, you give it the original function, and you get 0 back, which is what we want. So the self-healing works, and it's using Clojure spec to apply similar principles as we saw in the mutation testing code base. We patch the code with some other code, and we can do that because of homoiconicity. Okay, so this I thought is like kind of intense. Like Clojure is a great language for creating terrifying robots. You can have a program that's broken and then it can just fix itself, but also really cool. But more seriously, Clojure spec emphasizes and enhances what homoiconicity in Clojure already gives us. So quick summary, we get, yes, extending our language with macros and DSLs, which is what everyone kind of hears, what thinks when they hear homoiconicity. But we also get to analyze our code really well, which means we get great development tools. We can generate code easily, which means we can do things like mutation testing, generative programming. And we can visualize code really well because we know how to visualize data and code as data. And probably many more cool things. I hope I convinced you that homoiconicity is Clojure's superpower. Thank you for listening. There are the slides.